Hi everyone, we are Team Blue and today we'd like to present our project COVID Detect and automatic COVID-19 testing solution. So the reason we make this project is that we realized there exists a huge demand for COVID-19 testing services. But conducting a convenient test directly on site requires a very complicated system with expensive assets and experienced laborers and unworthy investment for small or medium-sized organizations. Well, of course, they may ask their people to accept tests on their own. It leads to higher variable costs, more inconvenience, and some reliability concerns. So we think that they may benefit from a general testing solution that enables low fixed and variable cost, on-site convenience, and reliability at the same time. So we plan to construct an unmanned COVID-19 testing solution. Our main customers are organizations like governments, schools, companies, who want to provide testing services to people like local citizens, students, and employees. Upon agreement, we'll install our machines on customer sites, and our machine will be capable of 3 testing methods: PCR swab, PCR saliva, and antigen swab. So the sample collection is completely automatic, so no people are required on site. Antigen samples can be analyzed directly inside the machine, but PCR samples must be sent to our labs for further experiments. So assume that the university has a mandatory weekly COVID-19 PCR testing requirements for all the students. So it purchases the solution from us, and many testing machines are installed across the campus. A student walks to the machine, he taps on his university ID card, and the machine recognizes his identity. The machine asks him which type of test he wants. He selects PCR swab. The machine displays some instructions and warnings. He clicks on the button to acknowledge and continue. A robotic arm gets out of the machine, grabbing a swab, inserts into his nose, and moves around. The arm retracts back to the machine and the student leaves. And then the sample is safely processed, packed, and stored inside the machine. An employee retrieves the sample from the machine and transports it to our lab. And the lab technicians perform experiments on the sample. When the result is ready, they enter the result into our system, and the system sends the result to the university. So there are a few stakeholders for our project, which are customers, users, health regulators, suppliers, and manufacturers, and of course, our own employees. So this is a pretty complicated system, and we have many subsystems. But for sake of time, we'll only briefly introduce a few of them. And if you look at the interface document on the right, you can actually quickly understand the basic functions of each subsystem and the relationship between the subsystems and track the flow of physical objects or data. So here are a few requirements for the top-level user system. So like the machine must be operable in most inhabited environments around the world because we want to maximize the range of customers with different operating conditions. And the derived requirement could be that the machine must be able to withstand common temperatures and humidities. Also, the machine can be used by most people without any human guidance. We want the design to be accessible as possible, of course, but requiring human guidance will introduce unnecessary labor costs and just defeats our purpose of creating an automatic testing service. Also, the machine must be able to authenticate legal users because we only want users that belong to the user group provided by our customer to be allowed to request a test because unauthorized tests from outsiders will lead to unnecessary test costs paid by our customer. And the derived requirement could be that there must be some hardware to read identifications from the user. The machine must also allow the user to select a test type, and so the machine must also have some hardware to accept inputs from the user. Last but not least, the machine must also convey test instructions to the user. we expect the user to follow certain requirements before and during the testing process to ensure that the test is conducted effectively and safely, which means that the machine must have a reasonably large and clear display in order to show some visual information. So for the trade-off, we have the display, and we could use the same off-the-shelf LCD displays because they are just relatively cheap. But of course, one problem with that is that LCD screens generally have lower brightness compared to OLED, which could cause visibility issues under sunlight if our machine is installed outdoors. However, OLED has a shorter lifespan as just way too expensive for large screen sizes. And for user inputs, we could use touch inputs, so a touch screen, but it may not be that intuitive to use for people who have limited experience playing around with smartphones. And it's also less responsive if the screen gets wet, which could happen if the machine is installed outdoors. The best alternative could be to use a non-touching display and plus some physical buttons, but that will substantially restrict the flexibility of our future updates in the future. We have many risks, for example, like unusual weather conditions, which can happen in any places, and that may cause minor or medium damage to the hardware. And of course, to mitigate that, we could add like waterproof thermal insulation and some common capabilities to the machine. We could also have unauthorized user access, which is also possible due to design, software, or hardware vulnerability. And the severeness is actually pretty low because it will only cause a waste of task costs to the customer, but still just relatively inexpensive. And to mitigate that, we could enforce user authentication or do more code quality inspections. And we can also have power outage, which occasionally happens in places with less robust infrastructure. And if that happens, the machine will become inoperable before recovery. But we can simply avoid that problem by adding a UPS or an uninterrupted power supply as a power source backup. And for the metrics, for the exterior of the machine, we can have like operating temperature has a unit Celsius, and that measures the range of temperatures that the machine can operate normally. And that might be sufficiently wide to endure extreme weather conditions. And for electricity, we can have the power input in volt as frequency and hertz as frequency and volt as the voltage. And that measures a certain range of voltages and frequencies supplied by the outlet that the machine can accept. And that must conform to local standards so that we can avoid damaging the circuits. For display, we have maximum brightness measured by nits, and that will impact our display visibility, which is actually pretty important if our machine is installed outdoors and will be under sunlight.
Hi, I'm Rachel. I'm here to talk about the sampling system, which supports the core mechanism for the sampling process. This slide lists the requirements for the sampling system. First of all, the sampling system must be able to communicate with the storage and packaging system. It takes test kits and collection tubes and so on and so forth as inputs and output raw samples to these systems. Secondly, the sampling system must be able to perform tests safely and properly on users. You don't want dangerous or inaccurate tests. Then, the sampling system must be able to detect human faces and position of nose. This goes the same with the last one, because we want safe tests, and we don't want to poke the cotton swab to other places on the face. The sampling system must be able to communicate with the top-level user system. I call it the bidirectional signaling, which means it takes signal inputs of like which tests we need to perform and output signal of any error or problem generated. Then, the sampling system must be able to properly transfer a raw sample to the collection tube. This is for the PCR tests. And finally, the sampling system must be able to complete an antigen rapid test. Next slide, let's talk about the feasibility analysis. Here identified three major components: the robotic arm, the conveyor, and the fist detection program. The robotic arm should have a base and joint and a cotton swab holder motor. There are three motors here, and other parts are metallic segments. We needed to have a high flexibility and higher degree of freedom So we implemented a lot of motor, but with that high amount of motor, there could be a high possibility of motor failure, so we're getting stuck. So that's a big trade-off. Next, the conveyor transport the test kit from storage system to the user. The meter might have similar issues of failing, so that's another trade-off we need to consider. And finally, the face detection is implemented with a micro camera and a computer vision program and used to calculate the position of user's face and the nose on the face and so on and so forth. There could be calculation errors, which are really, really dangerous in many situations. And on the next slide, I'm going to talk about how to deal with these risks. I mainly identified three major risks that could happen. The first one is the robotic arm pushing too aggressively. You have really low possibility because we designed the holder to move really, really slowly. So the cotton swab should not be inserted very fast, but it could be very, very severe when it actually happened. It could threaten users' comfort or even safety or their life. So we need to add damping to the holder's movement track and maintain a very small current for the motor. Next, the robotic arm aim for incorrect location. Similarly, as this first one, it should have a low possibility because the detection software should have a really high accuracy, higher than their human counterpart. But it could also be very severe. And we added one more protection to this by adding in a abort button. When the user feel too uncomfortable, they can press the abort button and the whole sampling process would stop. And finally, the robotic arm getting stuck or broken. This should not happen very frequently either, but when it happens, it's not as severe as the previous two risks because the machine would just stop providing any service, but no people would be harmed. To solve that, we can test the motors and other components maybe every 2 weeks or 1 month and replace them whenever we feel there could be a potential failure. And finally, the metrics for the component, we use radian per second to measure the rotation speed for the robotic arm. It should move really smooth and fast because we want a very flexible system. Next, the abort button, we use millimeter to measure the diameter of it. It should be easy to press. It should be big and visible. And finally, the conveyor should have a high maximum speed for delivering the test kits.
Hi everyone, I'm Xiaoru and I'm introducing the packaging and storage system. So packaging system requires us to have enough space to store all the samples. We also need to have clear labels on the sample tubes and on the packages that collect batches of sample tube. We also need to satisfy sanitary and safety standard and have temperature and humidity control. As for storage system requirement, we need appropriate condition to keep the samples uncontaminated, arrange samples in order of the time arrived, meet sanitary standards again, and store the waste generated from the sample system. And this is our functions, implementations, and trade-off for our system. So for shock absorption, we need absorbent mat per box, and it may be expensive to buy, but it prevents the spill of possible COVID-positive samples. And for leak-proofing function, we decide to use HDPE wide mouth jar per box so that we can put the samples in batches inside the jar and move it or put it into logistics. So it might be unfriendly to environment, but it can be cleaned and reused after each process. And we also need to label the boxes so that we have the information on the box. Another option is that we can print the information directly on the box during the box manufacturing, but it will create extra cost and work for printing. As for storage system, we need to have temperature conservation, so we employ two scientific refrigerators. We also realize there's not much difference between freezers and refrigerators, so we just stick with the refrigerators. And here is the risk and the possibility, severeness, and our solutions. So we have the risk, the spill of samples, it's relatively low because it's done by the machine. However, if it's going to spill, it's going to cause very severe problems and the staff may be affected. So the solution is that we need to require the staff to wear personal protective equipment, and there are also risks for sample denaturing if the storing time is too long. So if this is going to happen, we need to recollect the sample, and to solve this problem, we need to require low storage temperature, and there's also risk of missing samples, and for example, the machine arms may stuck the samples and it cannot be collected due to the mechanical errors. It's unlikely to happen because we assume our design is well tested. However, if it's going to happen, the customers may not receive the result. To counter this problem, we need to count and record the number of samples. And there are also risks for our waste in the storage system because the people dealing with the waste may have direct contact with COVID positive swab and they might be infected. So we need to use BSL level 3 biohazard standard to build a waste storage system. And here is the components, metric, unit, and description. Here we listed the absorbent packing material and measured by absorbency, the secondary container measured by waterproof rating, insulating material by thermal conductivity, printer by revolution, and refrigerator by temperature, and biosafety level by the level standard 3.
My name is CU and I'm going to present about the remote subsystem. There are 3 main requirements associated with the remote system. The first is that it must be able to generate a sample ID based on user information in order to uniquely identify a sample among all samples and establish correspondence between sample and user. The second requirement is that the remote system must be able to retrieve employee ID given employee information in order to provide authorization. The third requirement is that it must have an interface for outside system to access a user's test result or stock level. Based on the functions of the remote system, we can perform feasibility analysis. In order to generate sample ID, we can use a random seed such as current time or user information, and then query the database to confirm the sample ID generated is unique. The trade-off is that the process may take multiple rounds in order to succeed with large number of samples. To establish correspondence, we can develop a one-to-one algorithm to convert employee or user information into ID and then store pairs such as sample ID to user ID into database for query. The trade-off is that the algorithm may have flaws and the database may need frequent update with large number of samples. To ensure API access from outside system, we can receive requests and return the desired result by querying database or stored information. The trade-off is that the outside system may send multiple requests simultaneously, which requires strong ability for the system to process data concurrently. There are also certain risks associated with the remote system. The first risk is algorithm flaw. It will result in wrong information stored in the system or user unable to update or retrieve information. We can prevent this by adding a rigorous testing process before an algorithm is deployed. The second risk is database failure. It will result in data loss and needs time for recovery, and the whole system may also shut down. We can prevent this by adding a backup database to back up the new information from time to time. The third risk is server failure. The whole system might also shut down, and it will also result in database data loss. We can resolve this by also adding data backup plan and use logs for recovery process. There are certain metrics associated with remote system in order to assess its performance. The first is the average response time measured in milliseconds. It's the average amount of time for server to respond to a request for service. The second metric is throughput, measured in number of queries per second. It measures how quickly the database is able to process incoming queries. The third is failure rate. It's the percent of failed test cases among all test cases. The algorithm must pass all test cases in order to be deployed.
Another subsystem that is critical in the operational phase is the maintenance system. So we would like the maintenance system to perform software updates. So one of the requirements is going to be the system software must be able to be updated quickly and conveniently. Also, one of the maintenance system to track the stock and capacity information and warn the remote system if applied. The maintenance system must notify the remote system if the storage capacity is very high or the testing case stock capacity is very low. Then the machine should enable maintainers to perform fix physically. So the machine must have an easily accessible maintenance store for maintenance, and the maintenance system must get authentication from the remote system to verify the identity of the maintaining employees. So there are multiple trace study we've done here. For software update, we choose to have an over-the-air update because it can save a lot of time from going to the machine to update physically. Although there might be the cases that updates fail, which do require the maintenance to go to the machine physically to fix the problem. Then for the stock communication, we use stock and capacity information from the storage system and set a threshold for warning. Although the threshold may not be suitable at first, but we can always change it to a very empirical value one. And for maintenance authentication, it takes time from authenticating from a remote system, but it is necessary for safety. Then we have some risk analysis here. For the first risk, we may have maintenance mistake. It is completely unavoidable because human errors are often unavoidable. However, it might not be that severe because any very noticeable damage will be spotted by the maintainers. And the solution will be mandate a detailed double-check procedure after the maintenance is performed. Then there might be physical damages to the maintenance store caused by human damage or weather. It is severe because the related maintenance work may not be performed. So we should list the maintenance store physical structure integrity as one of the checklist items for routine maintenance. Then for the technical metrics, for software update, we want to use second to measure software update speed, and we want to use a Boolean value to measure the testing kit out of stock flag. Then we want to use millimeter to measure the maintenance store size, which are three important metrics we use here.
So far, we have identified business opportunities, conducted feasibility and risk analysis, and completed high-level requirements for the COVID detected system. We believe that the project is generally feasible from technical perspective. However, we still have many obstacles and uncertainties at this moment, where most of them arise from the sampling process. Though having a relatively small chance thanks to possibility safety measure, we are worried about the fully automatic sampling functions on noise. Unknowns could cause minor serious injuries to the users. As a result, we may not be able to obtain permission or certification from regulators to operate our business, which could lead to the halt of the entire project. In that case, if we are unable to gain a larger sum of funds extremely, we may not have sufficient funds to support design modifications for future design. Even if we are fortunate to establish our markets, we may not be able to afford serious consequences such as lawsuits or investigations caused by medical accidents. Thus, unfortunately, we recommend not to move on the next development phase at this moment. Instead, we recommend conducting more research on local requirements on medical equipment to further analyze the possible that our products will be permitted. Plus, more thorough feasibility and risk analysis must be performed, especially on the sampling subsystem to identify more potential safety issues of our design. Only after those we could have a clear picture of the situation and decide whether these projects should be rejected permanently.